Hello everyone, my name is Yash Yadav and my enrollment number is DE240229 and I am a student of International Institute of Professional Studies, DAVV Indore, and the subject is Numerical Analysis and Design. This video covers my first assignment, which asks us to write algorithm, to draw flowcharts, analyze time and space complexity, and give geometrical interpretations for numerical methods across 7 major topics. So let us go through each one. Section 1 covers 5 methods for finding the roots of polynomial equations, meaning we want to find values of x where f of x equals 0. So before each algorithm, I will state the assumptions I have taken as required by the assignment. So bisection method. So here the assumption that I have taken here, f is continuous on the closed interval from a to b. The product of f of a and f of b is negative, meaning the function has opposite signs at the two endpoints. So by the intermediate value, theorem at least one root exists in between. We also assume there is exactly one root in the interval, and a tolerance epsilon greater than 0 is given. The formula is simply the midpoint, where c equals a plus b divided by 2. The algorithm works like this. First, check that f of a and f of b have opposite signs. If not, stop, because we have no guarantee of a root. Then compute c, the midpoint. If the function value of c is smaller than our tolerance epsilon, we stop and report c as the root. Otherwise, we check which half of interval still contains the root by looking at the sign of f of a times f of c. If that product is negative, the root is in the left half, so we move our b to c. If it's positive, the root is in the right half, so we move a to the c. We keep having the intervals until we are close enough. Our geometrical interpretation. Imagine plotting of f of x and marking the 2 points A and B, where the curve is on opposite side of the x-axis. We keep finding the midpoint and checking which half still straddles 0. The interval literally halves each time, so after n iterations, the error is at most the original width divided by 2 to the power n. The time complexity is O of log base 2 of b minus a over epsilon. Space complexity is O of 1. The order of convergence is 1, meaning linear. This method is guaranteed to converge, which is the biggest strength. Now moving toward Regula-Falsi method. So in Regula-Falsi method, we have taken assumption same as bisection, where f continuous f of a times f of b negative. Additionally, we assume f is not excessively flat near the root to avoid the one-sided stagnation problem. The formula for the new point of c is c equals a minus f of a times b minus a divided by f of b minus f of a. This is the x-intercept of the straight line connecting the 2 points a f of a and b f of b. The algorithm is same as bisection except that instead of taking the midpoint, we take the chord intersection. We then replace the endpoint that has the same sign of f of c. Just like bisection, one important note. Unlike bisection, one endpoint can get stuck and never move. This is a known limitation. So, geometric interpretation. We draw a straight chord from a, f of a to b, f of b. So where our chord cuts x-axis, there we make a new point C. In bisection, we always pick geometric midpoint, but Regula-Falsi picks slope-weighted midpoint, usually which is closer to the root for smooth curves. One endpoint can get stuck forever if f is very curved. It is faster than bisection, but not guaranteed. Say our time complexity is O of n, which is faster than bisection for smooth functions. Space O of 1. Order of convergence is 1. means linear, though in practice it often behaves super linearly. Okay, so now moving towards secant method. In secant method, so we are taking assumption. We have two distinct initial guesses, x0 and x1. F of x0 is not equal to f of x1 to avoid division by 0. F is smooth near the roots. No bracket is required. This method does not need the function to have opposite signs at the 2 points. Now the formula is x of n plus 1 is equal to xn minus f of xn times xn minus xn minus 1 divided by f of xn minus f of xn minus 1. In algorithm, in each step, we compute f at both current points. We check the difference is not near 0. We compute the next guess using the formula. We check convergence, then shift. The old x1 becomes the new x0 and the new x2 becomes the new x1. We continue until converged. For geometric interpretation, at each step we draw a secant, a straight line through the last two computed points. Where the secant crosses the x-axis is the next guess. This approximation Newton's method by using a finite difference instead of true derivative. Both at points always move unlike Regula-Falsi. Our time complexity is O of n, space complexity is O of 1, order of convergence is 1.618, the golden ratio, which is between linear and quadratic. No derivatives is needed, which is a majorly practice advantage. Moving toward Newton-Raphson method. Newton-Raphson method, our assumptions. F is differentiable near the root. The derivative f prime of x is not 0 near the root. The initial guess x0 is sufficiently close to the root. F doubled prime exists for convergence analysis. The formula is x of n plus 1 equals x of n minus f of xn divided by f prime of xn. This is the x-intercept of the tangent line to the curve at the current point. Algorithm: we compute f and f prime at the current point. If f prime is near 0, stop. Flat tangent means trouble. Otherwise, compute the next guess. If the change is smaller than epsilon, stop and report the root. Otherwise, update and repeat. Our geometric interpretation: at point x of n, f of xn, draw the exact tangent to the curve. The tangent equation is y minus f of xn equals f prime xn times x minus xn. Setting y to 0 gives xn plus 1. Each step uses the actual slope of curve, much more information than the secant of bisection method use. The error squares each step. One correct digit becomes 2, then 4, then 8. Our time complexity is O of n, typically only 4 to 6 iterations for engineering accuracy. Space complexity is O of 1. Order of convergence is 2. It is quadratic, the fastest of all derivative-free class methods. The key downside is needing f prime and potential divergence from a bad initial guess. Moving towards fixed point iteration method. In fixed point iteration method, we are taking assumption. The equation of f of x equals 0 has been algebraically rearranged to the form x equals g of x. The contraction condition is satisfied. The absolute value of g prime of x is less than 1 in the region of interest. The initial guess x0 is in the wide range. The formula is simply xn plus 1 equals g of xn. We just keep applying g repeatedly. Algorithm: we verify the contraction condition near x0, compute x1 equals g of x0. If the absolute difference between x1 and x0 is less than epsilon, stop and report x as the fixed point. Otherwise, set x0 equal to x1 and repeat. Our geometric interpretation: we plot the diagonal line y equals x and also plot y equals x on the same axis. The intersection of these two curves is exactly the fixed point x star, where x star equals g of x star. Starting at x0 on the x-axis, we go up to the curve of y equals g of x, then horizontally across to the diagonal line to read off x of n plus 1. This creates a staircase pattern. When the absolute value of g prime is less than 1, the staircase spirals inward, which is converging. When it exceeds 1, the staircase spirals outward, means diverging. Now its time complexity is O of n, space complexity is O of 1, order of convergence is 1, which is linear for contraction mapping. The entire success of the method depends on choosing a good g of x. Section 2: Interpolation Methods. This section covers 5 interpolation methods. Interpolation means, given a set of data points, find a polynomial that either passes through all of them or can be used to estimate value at new positions. So first is Lagrange interpolation. Assumptions: we have n plus 1 distinct data points, xi, yi. The x values are all distinct, no duplicates. The query point t is within or reasonably near the data range. The method works for unequally spaced data, which is major advantage. The formula of P of t equals the sum over I of yi times Li of t, where each Li of t is the product over all j not equal to I of t minus xj divided by xi minus xj. Each Li is a basis polynomial that equals exactly 1 at xi and exactly 0 at every other data points. Algorithm: for each I from 0 to n, compute the numerator by multiplying t minus xj for all j not equal to 1 I, and compute the denominator by multiplying xi minus xj for all j not equal to I, and divide and multiply by yi, and sum of all the contributions. Geometric interpretation: the result is the unique polynomial of minimum degree that passes through all given points. The Lagrange basis function Li each contributes exactly the amount needed to hit the right y value at x. An important property worth noting: the sum of all Li of t equals 1. For any t, the Lagrange coefficients always sum to unity. This is proven by applying the formula to the constant function f equals 1. Now time complexity is O of n squared and space complexity is O of n. It works for any node spacing, unlike Newton's difference formula, which requires equal spacing. Hermite interpolation. Assumption: we have n plus 1 data points with both function values fxi and derivative values f prime xi known at each node. This gives 2 times n plus 1 conditions total, which uniquely defines a polynomial of degree at most 2n plus 1. The Hermite polynomial uses doubled nodes. We create a new node array where each xi appears twice. When we compute the divided difference table with the doubled array, whenever two adjacent nodes are the same, that is, the repeated node, we use f prime xi as the first divided difference instead of usual formula. The algorithm creates z array by setting z of 2i and z 2i plus 1 both equal to xi for each I. We build the divided difference table using the z array, inserting f prime values for each node pairs, evaluating using Newton's form at the query point. Geometric interpretation: Lagrange interpolation passes through all the data points. Hermite interpolation additionally matches the slope, the tangent direction, at each data point. So the curve is not just touching the data, it is tangent to the correct direction at every node. This is used extensively in computer graphics, animation, and spline-based curves where smoothness is critical. Now the time complexity is O of n squared, space complexity is O of n squared for divided difference table. It matches twice as many conditions as Lagrange. Divided difference table. Assumptions: n plus 1 distinct data points xi, yi nodes need not be equally spaced. This table is the foundation of Newton's divided difference interpolation formula. Algorithm: we initializes the table with fi0 equals yi for all I, then for each order k from 1 to n, for each row I from 0 to n minus k, we compute fik using the recursive formula. The diagonal entries f00, f01 all the way to f0n are the Newton's polynomial coefficients. For geometrical interpretation, the first divided difference is an average slope, change in y divided by change in x. The second is the rate of change of slope, like the second derivative scaled by factorial. The kth divided difference approximates the kth derivative divided by k factorial. One practical gem: if we add a new data point, only new diagonal entries need to be computed. The rest of the table stays the same. Now the time complexity is O of n squared to build. Space complexity is O of n squared for the full table. O of n if we only store the diagonals, and evaluation by Euler's method is O of n. Forward and backward difference table. Assumptions: data must be on equally spaced nodes with constant step h. Delta denotes the forward difference operator. Nabla denotes the backward difference operator. Forward difference operator: delta yi equals yi plus 1 minus yi. Second order: delta squared yi equals delta yi plus 1 minus delta yi. The pattern continues for the higher orders. Algorithm: we initializes di0 equals yi for each order k from 1 to n. For each I from 0 to n minus k, we compute dik equals di plus 1 k minus 1 minus dik minus 1. The result d0k for each k gives delta to the k of y0, the top diagonal entry at each column. A very useful detection property. If the nth order differences are all 0, the data is exactly a polynomial of degree less than n. If they are approximately constant, the data is approximately a degree of n polynomials. This is how we determine the degree of the underlying function from the data table alone. Time complexity is O of n squared. Space complexity is O of n squared for the full table, only valid for equally spaced data. Newton interpolation formula. Assumption: equally spaced nodes for the forward formula. Our S equals t minus x naught divided by h. For the backward formula, S equals t minus x minus n divided by h, where S is typically negative for points near the end of the table. The Gregory-Newton forward formula: the P of t equals y naught plus s times delta y naught plus s minus 1 over 2 factorial times delta squared y naught, and so on. The Gregory-Newton backward formula uses the same idea, but with nebular differences and s plus 1 type factors. Algorithm for forward formula: we build the difference table, compute s, start with result equals y naught, use a running product variable that accumulates s times s minus 1 times for each term divided by the factorial, multiply by corresponding diagonal difference, and add to result. Now which formula to use? Forward is most accurate when the query point is near the beginning of the data table, because That is where the forward differences are most reliable. Backward is most accurate near the end of the table, and central formulas like Stirling and Bessel's are best near the middle. Time complexity is O of n squared to build and O of n to evaluate. Space complexity is O of n squared only for equally spaced data. That is the critical constraint. Section 3, which is numerical differentiation. Our first is numerical differentiation, interpolation based methods. Our assumption, we have data points xi, fxi. We fit an interpolating polynomial p of x through the data and then differentiate the polynomial analytically. The accuracy depends entirely on how well the polynomial represents the true function. The idea, since f of x is approximately p of x, f prime of x is approximately p prime of x, and f double prime of x is approximately p double prime of x. So for Lagrange based differentiation, we differentiate each basis function Li analytically. The derivative L prime I at a point t is computed by the product rule applied to the product of t minus xj for all j not equal to I. Then f prime of t is approximately by the sum of yi times L prime I of t. So our geometrical interpretation is the true derivative is the slope of f of fx at a point. We draw a smooth polynomial curve through the data points and then measure the slope of that curve instead. The accuracy depends on how faithful the polynomial is to the true function. Okay, so there's an important warning. The differentiation amplifies oscillations. For large n with equally spaced nodes, Runge phenomena can cause the polynomial to oscillate wildly between data points, making the derivative very inaccurate. So using fewer points to space nodes reduce the risk. So our time complexity is O of n squared, space complexity is O of n, error proportion to h to the n for an nth order method. Finite difference method. Assumption, equally spaced node with step h, function values known at grid points. The step h must be small enough to reduce truncation error, but not so small that the round of error dominates. There are three main finite difference formulas for the first derivative. The forward difference f prime of x is approximately f of x plus h minus f of x divided by h. This has error of order h. The backward difference f prime of x is approximately f of x minus f of x minus h divided by h. Also error of order h. The central difference, the f prime of x is approximately f of x plus h minus f of x minus h divided by 2h. This has error of order h squared, which is much more accurate, and it is the preferred formula whenever both neighboring points are available. For the second derivative, f doubled prime of x is approximately f of x plus h minus 2 times f of x plus f of x minus h divided by h squared. This has error of order h squared. Our algorithm gives function value at a grid at interior index I, which compute f of prime of xi as fi plus 1 minus fi minus 1 divided by 2h, and f double prime as fi plus 1 minus 2 times fi plus fi minus 1 divided by h squared. So our time complexity is O of 1 per grid point. The space complexity is O of 1. Always use central differences when available. The O of h squared error versus O of h makes a substantial difference in accuracy. Section 4, which is numerical quadrature, integration. Here we have Newton-Raphson formula. Our assumptions, equally spaced nodes with step h. F is integrable on the interval from a to b. For Simpson's rule, the number of intervals n must be even. For Wheeler's rule, n must be a multiple of 6. The three main functions in the family. First, the trapezoidal rule. The integral is approximated as h divided by 2 times y naught plus 2y 1 plus 2y 2 plus dot 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 plus 2y n minus 1 plus y minus n. Sorry, y of n. The coefficient pattern is 1, 2, 2, comma, all the way to n minus 1 term to 2 and then n term is 1. This fits a linear polynomial straight line in each subinterval. Error of order h squared per step. Second, Simpson's one-third rule. The integral is h divided by 3 times. Y naught plus 4y, 1 plus 2y, 2 plus 4y, 3 plus and all the way to plus y minus n. So our coefficient patterns is 1, 4, 2, 4, 2 all the way to 4, 1. This fits a quadratic polynomial through each pair of subintervals. The error of order h to the 4. Third, the Wheeler's rule. The integral is 3h divided by 10 times y naught plus 5y, 1 plus y, 2 plus 6y, 3 plus y, 4 plus 5y, 5 plus y, 6. So the coefficient are 1, 5, 1, 6, 1, 5, 1. The sum equals 20. This fits a degree 6 polynomial across 6 subintervals. So the error of order h to the 8, which is extremely accurate. So the algorithm for composite Simpson's 1 by 3, we compute h equals b minus a over n. Start with sum equals f of a plus f of b for each interior point I from 1 to n minus 1. If I is odd, add 4 times fa plus I times h. If is even, add 2 times fa plus I times h and multiply the total sum by h divided by 3. Our geometrical interpretation says each method replaces the true curve in each subinterval with a simpler shape. Trapezoidal, straight line, trapezoid. Simpson's parabola, curvy but smooth. Wheeler's degree 6 curve, even more faithful. The area under the simpler shape is easy to compute exactly. The time complexity is O of n for all three. Space complexity is O of 1 as the error order increases for the h square to the h to the 4 to h to the 8. Each method needs fewer intervals to achieve the same accuracy. Gauss Quadrature formula. Assumptions. F must be smooth on the interval. The standard form works on -1 to 1. For a general interval from A to B, we use the variable transformation x equals b minus a over 2 times t plus a plus b over 2. The nodes and weights come from standard pre-computed tables. The formula. The integral from -1 to 1 of f of t dt is approximately the sum over I of wi times f of ti, where ti are the nodes and wi are the weights. For a general interval, we scale by v minus a divided by 2. The algorithm. Look up the tabulated nodes ti and weight wi for the chosen number of point n. Transform each node to the actual interval using the formula xi equals b minus a over 2 times ti plus a plus b over 2. Sum of wi times fxi for all I and multiply by b minus a over 2. So our geometrical interpretation. The Newton-Raphson method places evaluation points equally spaced, a human-friendly choice. But Gauss quadrature asks a deeper question. What are the optimal positions to the sample f? Ones that gives the highest possible accuracy. The answer is the roots of Lagrange polynomial. By choosing these special positions, clustered toward the center and endpoints, and pairing them with careful computed weights. The formula is exact for polynomials of degree up to 2n minus 1. So 4 Gauss points give exact result for any degree 7 polynomial. The time complexity is O of n, space complexity is O of 1, exact for polynomials of degree up to 2n minus 1, which is far superior to Newton's quadrature for the same number of function evaluations when f is smooth. Section 5, which is linear equations, Gauss Elimination Method. Assumptions: n by n non-singular matrix A. Partial pivoting is applied to avoid division by near zero values. The system has a unique solution, meaning the determinant of A is non-zero. The method has two phases. Phase 1 is forward elimination, which reduces the matrix to upper triangular form. Phase 2 is back substitution, which solves from the last row upward. Algorithm: we work on the augmented matrix AB of size n by n plus 1. For each column k from 0 to n minus 1, first find the row with the largest absolute value in the column k at or below row k, and swap that row with row k. This is partial pivoting. Then for each row I below k, compute the factor as a ik divided by a kk, and subtract the factor times row k from row I. After all columns are processed, the matrix is upper triangular. Then back substitute for I from n minus 1 down to 0. Xi equals bi minus the sum of aij times xj for j greater than I divided by a ii. And our geometric interpretation: each equation ax equals b represents a hyperplane in n-dimension space. The solution is the single point where all n hyperplanes intersect. Forward elimination systematically rotates and scales the hyperplanes until the system looks like a staircase. Each equation has one fewer unknown than the previous. Back substitution then easily reads off the solution from the bottom step upward. The time complexity is O of n cubed, space complexity is O of n squared. The direct method gives the exact answer in a single forward-backward pass, subject only to floating point round-off, and partial pivoting is essential for numeric stability. Jacobi iteration method. Assumptions: the matrix A is strictly diagonally dominant, meaning for each row I, the absolute value of aii is greater than the sum of absolute values of all other entries in that row. This guarantees convergence. An initial guess vector x naught is provided. The update formula: xi at iteration k plus 1 equals bi minus the sum of aij times xj at iteration k for all j not equal to I divided by aii. The critical point: all the xj values used here are from previous iteration. We do not use any updated values during the current swap. The algorithm: we need two vectors, x old and x new. In each iteration, for each row I, compute sigma as the sum of aij times x old j for all j not equal to I. Then x new I equals bi minus sigma divided by aii. After computing all x new values, check convergence. If the maximum absolute difference between x new and x old is less than epsilon, stop. Otherwise, copy x new into x old and repeat. The geometric interpretation: each equation in the system defines a hyperplane. The iteration projects the current guess onto each hyperplanes one by one, using only old information. Because all updates are independent, Jacobi is easily parallelizable. All n updates in each iterations can be done simultaneously on separate processes. The time complexity is O of k times n squared, where k is the number of iterations. Space complexity is O of n squared for the matrix plus O of 2n for the two vectors. Gauss-Seidel method. Assumption: same as Jacobi, diagonally dominant, asymmetric positive definite matrix. The key algorithmic difference is that new computed values are used immediately rather than waiting for the next iteration. The updated formula: xi at iteration k plus 1 equals bi minus the sum of aij times xj at iteration k plus 1 for j less than I minus the sum of aij times xj at iteration k for greater than I divided by aii. In plain language, when computing xi, use the most recently computed value of x1 through xi minus 1, even though there was just updated the same iteration. Algorithm: so only one vector is needed for each row I from 0 to n minus 1. Computed sigma as the sum of aij times xj for all j not equal to I. Since xj for j less than I was already updated in this iteration, those newer values are automatically used. Then xi equals bi minus sigma divided by xii. We check convergence with each full sweep. The geometrical interpretation: it is exactly the same hyperplane projection idea as Jacobi, but with an important improvement. As soon as we compute a better approximation for x1, we immediately use it to compute x2, rather than waiting until the next iteration. It is like adjusting your recipe as you cook, rather than adjusting it before you start the next batch. This typically halves the number of iterations needed compared to Jacobi. The time complexity is k times n squared. Space complexity is of n squared for the matrix O of n for just one vector. It is approximately twice as fast as Jacobi in terms of iteration, but not parallelizable. Approximation methods. Least squares approximation. Assumptions: we have m data points where m is greater than n plus 1. More data points than unknowns. We want to fit a polynomial of degree n. The system is overdetermined, so we cannot pass exactly through all points. Instead, we minimizes the sum of squared residual. Our objective is to minimize E equals the sum of yi minus p of xi squared over all I, where p of x is our polynomial. Setting the partial derivative of E with respect to each coefficient aj to 0 gives the normal equation. Algorithm: build the n plus 1 by n plus 1 normal equation matrix. Entry aij equals the sum over k of xk to the power I plus j. The right hand side bi equals the sum over k of yk times xk to the power I. We solve this symmetrically system using Gauss elimination to find the coefficients a0 through an. The best fit polynomial is then the sum of aj times x to the j for j from 0 to n. Geometric interpretation. Think of it this way: interpolation draws a curve that passes exactly through every data point, including all the noise and measurement errors in the data. Least squares instead draws a smooth curve that is as close as possible to all the points simultaneously. Minimizing the total squared vertical distances. Squaring means large errors are penalized much more than small ones, encouraging the curve to avoid extreme outliers. For noisy real-world data, this gives much more reliable result than interpolation. So the time complexity is O of m times n to build the normal equation or plus O of n cubed to solve them. Space complexity of n squared, the result minimizes the error but does not eliminate it. Polynomial approximation using orthogonal polynomials. Assumptions: f is continuous on the interval from a to b. We choose an orthogonal polynomial basis such as Lagrange polynomial for the interval -1 to 1. An inner product is defined using a weight function w of x. So the formula f of x is approximated by the sum of ck times pk of x from k equals 0 to n. Each coefficient ck equals the inner product of f and pk divided by the inner product of pk with itself. In terms of integrals, ck equals the integral of f of x times pk of x times w of x dx divided by the integral of pk squared times w of x dx. Algorithm. We choose the orthogonal basis appropriate for the interval and weight. For each k from 0 to n, we compute the numerator and denominator integrals using Gauss Quadrature. Divide to get ck. The approximation is then the linear combination of these basis polynomials. Geometrical interpretations. Think of functions as vector in an infinite dimensional space. Orthogonal polynomials p0, p1, p2 and so on are like the xyz axes. They are mutually perpendicular in the sense of the inner product. Each coefficient ck is the projection of f onto the kth axis direction. Standard least squares uses the monomial basis 1 x squared. These are not orthogonal to each other, which causes the normal equation matrix to become extremely ill-conditioned for large numbers. Orthogonal basis polynomials completely avoid this problem. A beautiful bonus. Okay, adding a higher degree term does not change any previously computed ck values. The coefficients are independent. So the time complexity is O of n times q, where q is the cost of one quadrature integral, and the space complexity of O of n, numerically stable, highly recommended over standard least squares for high degree approximations. Now the section 7 is ordinary differential equations. Euler method. Assumptions. The ODE is dy over dx equals f of x comma y, with initial condition y of x naught equals y naught. F is Lipschitz continuous. It guarantees a unique solution exists. The step size h is small enough that the solution does not change dramatically over one step. The formula states yn plus 1 equals yn plus h times f of xn comma yn. The value advances as xn plus 1 equals xn plus h. The algorithm: set x equals to x naught and y equal to y naught. While x is less than xn, compute the slope as f of x comma y. Update y to y plus h times slope. Update x to x plus h. Record the pair x comma y. Repeat until we reach xn. The geometric interpretation. The ODE tells us the slope of the true solution curve at any point x comma y. At the current position xn comma yn, Euler's method reads the exact slope from the ODE and then takes a straight line step of the length h in the direction to estimate yn plus 1. The true solution curves away from this tangent line immediately, so the method accumulates error. The analogy is hiking by compass bearing in hilly terrain. You follow a straight bearing between checkpoints, but the actual shortest path curves smaller steps means you check your compass more often and stay closer to the true path. The time complexity is of O of n, where n equals x n minus x naught divided by h. Space complexity is O of 1 if streaming, and O of n if storing local truncations error O of h squared. Global error O of h, first order method. Halving h halves the total error. Runge-Kutta fourth order method. Assumptions: same ODE structure, dy over dx equals fx comma y, with initial condition yx naught equals y naught. F has continuous partial derivatives up to fourth order. The step size h is chosen for stability. This method takes 4 slope measurements per step. K1 equals h times fxn comma by n, the slope at start. K2 equals h times f of x n plus h over by n plus k1 over 2. The slope at midpoint using k1 to estimate the midpoint y. K3 equals h times f of x minus 1 plus h over 2 by minus n plus k2 over 2. The slope at the midpoint again, but using the improved estimate k2, k4 equals h times f of xn plus h, comma yn plus k3. The slope at the end of the step using k3 as the estimate. The final update: yn plus 1 equals yn plus k, 1 plus 2k, 2 plus 2k, 3 plus k4, okay, divided by 6. This is a weighted average. The midpoint slope k2 and k3 get doubled weight because they represent the middle of the step, like Simpson's rule in integration. Algorithm: set x to x naught, y to y naught, while x is less than xn. Compute k1, k2, k3, k4 using the formula above. Update y equals y plus k1 plus 2k, 2 plus 2k3 plus k4 divided by 6. Update x equals x plus h and repeat. The geometric interpretation: Euler uses one slope measurement only, the starting slope, and takes a straight line step. The Runge-Kutta method uh, uses 4 careful chosen slope samples across the step interval, 1 at the start, 2 at the midpoint using the progressively better estimates, and 1 at the end. It then combines them with weights that mirror Simpson's rule. This gives a much more accurate average slope for the entire step, meaning the curve followed is much closer to the true solution. The global error is O of h to the 4, so halving h reduces the error by the factor of 16 compared to only a factor of 2 for units. The time complexity is O of n steps with 4 functions evaluations per step. Space complexity is O of 1. Global error is O of h to the 4, far superior to the Euler's. This is the most widely used single-step ODE solver in practice because it balances accuracy and simplicity elegantly. So this is the complete complexity summary which you can use for the future references. Thank you for watching the video. Hope this presentation gave you a complete and clear understanding of all 7 topics in the first assignment. Thank you.